All right. So in our last video, we talked about how change in magnetic fields cause a current, and we just talked about the direction of the current and what's going on. So in this video, we're going to talk about how to calculate what the current is going to be, and there's going to be some equations we're going to use and some definitions. All right. Now, first off, there has to be a change in flux. So flux. The symbol for flux is going to be the Greek letter phi, and that's going to be the magnetic field times the area. And that is flux. Then we got this equation, and there's a new variable. It's this curly E equals N change in flux over change in time. So we have to have a change in flux for this to occur. The curly E thing is called electromotive force. Or EMF. But it's really just voltage. Okay, for some reason these are different symbol for it when we're dealing with a magnetic induced current, but this is just going to give us our voltage. And then once we have the voltage and we want a current, we have to remember this equation from our current unit. And I is current, and R is resistance. And I didn't define the N up here. And N is the number of turns in the coil. Remember I said if you have 100 turns in your coil, you're going to have 100 times as much effect. So I'm going to post a reference table that has all the equations on it for this unit, but here they are in the notes. So we're going to do two examples. Our first example, we have a coil of wire of 50 turns. So let's start making a list of variables. So we're going to have N is 50 turns. And an area of 0.01, so that's A. Area is in meters squared. Resistance of 240 milliohms. Now milli is 10 to the minus third, so I would move 3 places. So that's going to be 0.240 ohms for R. And then at first there's no magnetic field and it increases. So we'll have to pay attention to that in a bit. And the magnetic field at the end is going to be 4 Tesla. And it's turned on in 0.01 seconds. And we want to know current. All right, so there's going to be several steps to this. All right, so first I'm going to find the amount of flux by doing B times A. B is 4. A is 0.01. This was Tesla. This is meters squared. So the flux is going to be 0.04, and the unit for it is Tesla meters squared. So there's that. All right, then I'm going to find the EMF, or the voltage generated, by using this equation. So N is the number of turns, was 50. And the change in flux is going to be 0.04 because it starts at 0 because there's no field, and then it's turned up to 4 for the magnetic field, which gives us a flux of that. And then divided by the time, and the time is, if I have that wrong, it's 0.1 seconds. When I calculate this out, I get 20 volts. Now we didn't just want the voltage, we want the current. And so now I have to use V equals IR. And this electromotive force is the same thing as voltage, so I can plug it in there. So 20 equals I times 0.240. because our R up here was 0.240, and I end up with a current of 83.3 amps. Now that's the amount. We still need to find the direction based on what we did last time. So we'll put over here direction. So here we said it's increasing, and dots mean it's out. So the change in magnetic field, or in magnetic flux, is to increase out. Then we have to resist that. And we resist it by either decreasing out or increasing in. Those would be the opposites. We want to choose the increase every time. So increase in is the opposite of that. And that tells us we're going to point our thumb into the page. So the current, if we point our thumb into the page, is going to be clockwise. All right, because my fingers are curling around clockwise. So our net answer altogether is that I is 83.3 amps clockwise. And our last example is this here. So now I have a single loop. If I have a loop, it doesn't have a whole bunch, it's just one. So N is going to equal 1. We got our resistance here. Milli means move it 3 places, so it's going to be 0.03 ohms. And then we got the area here. Area is 4 times 10 to the minus 6th. Magnetic field is 4 Tesla. It's going to rotate 90 degrees. That's going to make it turn like this. So it's going to make the flux turn off. And the time is 0.001 seconds. And this is a very similar question. We're trying to find the current. So first we'll find the flux. B is 4 and times 4 times 10 to the minus 6th. And I end up with 1.6 times 10 to the minus 5th Tesla meter squared for the flux. The second step is to find the EMF. Again, since it's just a single loop, N is going to be 1. The flux is 1.6 times 10 to the minus 5th. Divided by 0.001, and that's going to give me electromotive force, or EMF, of 0.016 volts. And then we're going to plug that into V equals IR. 0.016 is I times 0.03 for our R, which we had up here, and we end up with a current of 0.53 amps. Then we have to find the direction again. So in this case, when I flip it 90 degrees, right now all of the flux is going through it. When I turn it 90 degrees, none of it will. So I'm decreasing. So my change is to decrease the flux, and the X is mean into the page. To resist that, I have to do the opposite. I have to increase the in or decrease the out. We change the increase, or we pick the increase. This is telling me to point my thumb in. So the current is going to equal, if my thumb goes in, the current is going to be clockwise.